Welcome to this coding walkthrough. In this session, we'll tackle LeetCode problem number 1230, toss strange coins. This problem challenges us to calculate the probability of getting exactly a certain number of heads when tossing coins with varying probabilities of landing heads. It's a fascinating exercise in probability and dynamic programming. Let's dive into the details and break it down step by step. In this problem, you are given a set of coins, each with its own unique probability of showing heads when tossed. These probabilities are represented as a list of decimal values, where each value lies between 0 and 1, inclusive. The task is to calculate the probability that, after tossing all the coins, the exact number of heads observed equals a given target value. For the input, you will receive two pieces of information: the list of probabilities, which we'll call prob, and the target number of heads, which is an integer. The output will be a single floating point number representing the probability of achieving exactly that number of heads, and it will be considered correct if the absolute error is less than 10 to the power of -5. This means we need a precise computation to ensure the result falls within this margin of error. Now, let's examine an example to solidify our understanding of the problem. Consider this example: the list of probabilities is 0.5, 0.5, 0.5, and the target number of heads is 2. This means we have 3 coins, each with a 50% chance of showing heads, and we want exactly 2 of them to show heads after all the coins are tossed. To compute this, we need to evaluate all possible outcomes. For these 3 coins, the outcomes include combinations like HHH, HHT, HTH, HTT, and so on. Each combination has a probability determined by multiplying the probabilities of heads or tails for each coin in that specific outcome. For instance, the probability of HHH is 0.5 asterisk 0.5 asterisk 0.5, which equals 0.125. By calculating the probabilities for all outcomes, we can identify which ones result in exactly 2 heads and then sum their probabilities to find the total result. Among the outcomes, the ones that give exactly 2 heads are HHT, HTH, and THH. For each of these, the probability is 0.5 asterisk 0.5 asterisk 0.5, which equals 0.125. Adding these probabilities together gives us the total probability of achieving exactly 2 heads, 0.125 plus 0.125 plus 0.125, resulting in 0.375. Now, let's consider a more complex example where the coins have different probabilities of showing heads. Suppose the list of probabilities is 0.3, 0.6, 0.8, and the target is again 2 heads. Here, each coin has a distinct likelihood of showing heads, so we need to carefully compute the probabilities for each valid outcome. To calculate the probability for this example, we identify all combinations that result in exactly 2 heads. For instance, one valid combination is when the first and second coins show heads, and the third shows tails. The probability for this is 0.3 asterisk 0.6 asterisk 1 to 0.8, which equals 0.036. Another combination is when the first and third coins show heads, and the second shows tails. The probability here is 0.3 asterisk 1 to 0.6 asterisk 0.8, which equals 0.096. Finally, if the second and third coins show heads and the first shows tails, the probability is 1 to 0.3, asterisk 0.6 asterisk 0.8, which equals 0.336. Adding these probabilities together gives the total probability of exactly 2 heads, 0.036 plus 0.096 plus 0.336, resulting in 0.348. To solve this problem efficiently, dynamic programming can be used. By defining dp, I, j, as the probability of getting exactly j heads using the first I coins, we can build a solution iteratively. Further, space optimization techniques can reduce the memory requirements to a linear scale, ensuring the solution remains efficient even for large inputs. To solve the problem of calculating the probability of getting exactly a target number of heads when tossing coins with varying probabilities, we considered multiple approaches. The first approach is the brute force method, where we enumerate all possible outcomes of the coin tosses. This involves simulating every combination of heads and tails and summing up the probabilities of the outcomes that match the target number of heads. While intuitive, this method is computationally expensive, requiring 2 to the power of n, time due to the exponential growth of combinations as the number of coins increases. This makes it impractical for larger inputs. The second approach uses dynamic programming to optimize calculations by avoiding redundant work. Here, we define a DP table, where DP, I, J, represents the probability of getting exactly J heads after tossing the first I coins. The key insight is to transition between states based on whether the current coin lands as heads or tails, using its associated probabilities. This method drastically reduces computational overhead compared to brute force by leveraging the recurrence relation to build solutions incrementally. The recurrence relation for the DP approach breaks down the possibilities for the current coin. It can either land tails, contributing a factor of 1 minus its probability, or it can land heads, contributing its actual probability. These two outcomes allow us to calculate the probability for each state in the table. The base case is straightforward. When no coins are tossed, the probability of getting 0 heads is exactly 1. The time complexity of this approach is O, n times target, since we process each coin across all possible target values. The space complexity is also O, n times target, because we maintain the full DP table. However, this can be optimized further. By observing that each state in the DP table only depends on the previous row, we can reduce the space complexity to O, target, by using a single 1D array and updating it in reverse order. This ensures that values from the previous iteration are not overwritten prematurely. This space-optimized DP approach retains the same time complexity but is significantly more memory efficient, making it ideal for larger datasets. Ultimately, the space-optimized dynamic programming approach was chosen as the final solution. This method strikes the right balance between efficiency and simplicity. It achieves O, n times target, time complexity and O, target, space complexity, which makes it scalable for larger inputs while avoiding the storage overhead of a full 2D table. Although the 2D DP approach is easier to visualize and debug, it is less memory efficient, and the brute force method is entirely impractical due to its exponential time complexity. The key insight that enabled this optimization was recognizing that the problem can be broken down into smaller sub-problems, a natural fit for dynamic programming. Transitioning to a 1D DP array was made possible by realizing that each state only depends on the previous one, and reverse iteration prevented overwriting critical values. These observations allowed us to create a solution that combines time efficiency, space efficiency, and implementation clarity, making it the optimal choice for solving this problem. In this problem, we're tasked with calculating the probability of getting exactly a certain number of heads, called the target, when tossing a number of coins, each with its own unique probability of landing heads. This is a classic dynamic programming problem, where we solve it by breaking it into smaller overlapping subproblems. To start, we define our state as DP, I, K, which represents the probability of getting exactly K heads using the first I coins. For our base case, DP 0, 0 is set to 1, meaning there is a 100% chance of having 0 heads when no coins are tossed. The transition formula then allows us to update this state. If we include the ith coin, it contributes to the probability of heads based on its specific probability, prob, I1. If we exclude it, the probability remains the same as before. The formula sums these two possibilities, where the first term accounts for excluding the coin, and the second term accounts for including it. This approach ensures that we efficiently account for all combinations of coins and head counts. To implement this algorithm, we first initialize a 2D DP table, DP, with dimensions n plus 1 is x, target plus 1. All values are set to 0 initially, except for the base case DP, 0, 0, equals 1. This sets up the foundation for our calculations. Next, we fill the table by iterating through all coins and all possible head counts. For each combination, we use the transition formula to compute the probability of achieving exactly K heads using I coins. Once the table is fully populated, the answer to our problem will be located at DP, n, target, which represents the probability of achieving the target number of heads with all n coins. This algorithm leverages the principle of optimal substructure, where the probability for K heads with I coins depends only on the probabilities calculated for the previous coin. Additionally, to optimize space usage, we recognize that each row of the DP table depends only on the previous one. This allows us to reduce the space complexity from O, n asterisk target, to O, target, by maintaining only 2 rows at a time. When solving this problem, we must handle several key edge cases. For example, if the target number of heads exceeds the total number of coins, it's impossible to achieve, so the result is 0. Similarly, if all probabilities are 0, meaning no coin can land heads, the result is also 0 unless the target is 0. Conversely, if all probabilities are 1, meaning every coin always lands heads, the result is 1 only if the target equals the number of coins. Regarding data structures, we use a 2D DP array to store probabilities for each subproblem, with dimensions n+1 each x, target +1. To optimize space, we can use a 1D DP array of size target +1, updating it in reverse order to avoid overwriting values. In terms of complexity, the time complexity is O, n** target, because we iterate through all coins and potential head counts. For space, the unoptimized version requires O, n** target, while the optimized version reduces this to O, target, by maintaining only the current state. To fully implement the space-optimized version of the algorithm, we start by initializing a 1D DP array of size target +1 with all values set to 0, except for DP, 0, which is set to 1 as our base case. Then, for each coin in the prob array, we iterate over the possible head counts in reverse order, from target down to 1. This reverse iteration is crucial to prevent overwriting values that are still needed for calculations. For each k, we update the probability using the formula dp k equals dp k asterisk 1 prob I1 plus dp k1 asterisk prob I1, which combines the probabilities of excluding and including the current coin. For the special case where k is 0, we update dp 0 as dp 0 asterisk 1 prob I1, since there's no contribution from heads. Finally, after processing all coins, the result representing the probability of achieving the target number of heads is found in dp target. This solution implements a dynamic programming approach to calculate the probability of getting exactly target heads after tossing in strange coins. Each coin has a unique probability of landing heads, given in the input list prob. We first initialize a 2D array dp where dp I, j, represents the probability of getting exactly j heads from the first I coins. The base case is straightforward, dp 0, 0 is set to 1 because the probability of 0 heads with 0 coins is 1, and all other dp 0, j values are initialized to 0. For each coin, from 1 to n, we iterate over the possible number of heads, from 0 to target. If we decide not to use the current coin, the probability remains the same as dp I1, j, multiplied by the probability that the coin lands tails, 1 prob I1. If we decide to use the current coin, we add the contribution from dp I1, j1, multiplied by the probability of the coin landing heads, prob I1. This ensures we account for both possibilities, using or not using the current coin. Finally, the desired result is stored in dp n target, which represents the probability of achieving exactly target heads using all in coins. This approach ensures that all overlapping subproblems are reused efficiently, avoiding redundant computations. The time complexity of the solution is O, n** target, where n is the number of coins and target is the required number of heads. The space complexity is also O, n** target, for the DP table. This implementation is robust and handles all edge cases effectively, such as when target is 0 or equal to the total number of coins. This is the Java implementation for LeetCode problem number 1230, toss strange coins. It follows the same dynamic programming logic as the Python solution, using a 2D array dp to store probabilities of achieving a specific number of heads with a given number of coins. Key differences include explicit type declarations for arrays and variables, and the Java-specific syntax for array initialization and loops. To solve this problem, we begin by initializing the dynamic programming table. Since we have 2 coins, the number of rows in the table will be n+1, which is 3. The target is 1 head, so the number of columns will be target +1, which is 2. This gives us a table with dimensions 3 by 2, initialized with all zeros. Next, we establish our base case. The probability of getting 0 heads with 0 coins is 1, so we set dp 0, 0 equals 1. Now, we process the first coin. When considering 0 heads, if the first coin is tails, the probability is given by dp 1, 0 equals dp 0, 0 asterisk 1 prob 0. Substituting the values, we find dp 1, 0 equals 1 asterisk 0.5, which equals 0.5. For the first coin, we now calculate the probability of getting one head. If the first coin lands heads, the probability is given by dp 1, 1 equals dp 0, 0 asterisk prob 0. Using the values, we compute dp 1, 1 equals 1 asterisk 0.5, which equals 0.5. At this point, the table updates to reflect these probabilities. dp 1, 0 is 0.5 and dp 1, 1 is also 0.5. Moving on to the second coin, we start with the case of 0 heads. If the second coin is tails, the probability is calculated as dp 2, 0 equals dp 1, 0 asterisk 1 prob 1. Substituting the values, dp 2, 0 equals 0.5 asterisk 0.5, which equals 0.25. Then, for the case of one head, we consider both tails and heads scenarios. If the second coin is tails, dp 2, 1 equals dp 1, 1 asterisk 1 prob 1, which computes to 0.5 asterisk 0.5 equals 0.25. Additionally, if the second coin is heads, dp 2, 1 plus equals dp 1, 0 asterisk prob 1, resulting in 0.25 plus 0.5 asterisk 0.5 equals 0.5. The updated table now reflects these values. The final value we are interested in is dp 2, 1, which represents the probability of getting exactly one head with two coins. From the table, we see that this value is 0.5. Now, let's consider a new example to further solidify this approach. For this example, we have three coins with probabilities 0.3, 0.6, 0.8, and a target of two heads. First, we initialize the dynamic programming table. Since there are three coins, the table will have n plus 1 rows, making it 4 rows. The target is two heads, so the number of columns will be target plus 1, giving us 3 columns. The table dimensions are 4 by 3, and we initialize all cells to 0. As before, the base case is dp 0, 0 equals 1, representing the probability of 0 heads with 0 coins. Next, we process the coins one by one. Starting with the first coin, which has a probability of heads equal to 0.3, we calculate the probabilities for 0 and 1 head. For 0 heads, the probability is dp 1, 0 equals dp 0, 0 asterisk 1 to 0.3, which equals 1 asterisk 0.7 equals 0.7. For 1 head, the probability is dp 1, 1 equals dp 0, 0 asterisk 0.3, which equals 1 asterisk 0.3 equals 0.3. The table now updates to reflect these probabilities. Moving to the second coin, which has a probability of heads equal to 0.6, we calculate probabilities for 0, 1, and 2 heads. For 0 heads, dp 2, 0 equals dp 1, 0 asterisk 1 to 0.6, which equals 0.7 asterisk 0.4 equals 0.28. For 1 head, dp 2, 1 equals dp 1, 1 asterisk 1 to 0.6 plus dp 1, 0 asterisk 0.6, which computes to 0.3 asterisk 0.4 plus 0.7 times 0.6 is equal to 0.18 plus 0.42 equals 0.6. For 2 heads, dp 2, 2 equals dp 1, 1 asterisk 0.6, which equals 0.3 asterisk 0.6 equals 0.18. The table updates accordingly. Finally, we process the third coin, which has a probability of heads equal to 0.8. For 0 heads, the probability is dp 3, 0 equals dp 2, 0 asterisk 1 to 0.8, which equals 0.28 asterisk 0.2 equals 0.056. For 1 head, dp 3, 1 equals dp 2, 1 asterisk 1 to 0.8 plus dp 2, 0 asterisk 0.8, which computes to 0.6 asterisk 0.2 plus 0.28 times 0.8 is equal to 0.12 plus 0.224 equals 0.344. For 2 heads, dp 3, 2 equals dp 2, 2 asterisk 1 to 0.8 plus dp 2, 1 asterisk 0.8, which calculates as 0.18 asterisk 0.2 plus 0.6 times 0.8 is equal to 0.036 plus 0.48 equals 0.516. The table is now complete, and the value we are interested in is dp 3, 2, which represents the probability of getting exactly 2 heads with these 3 coins. This value is 0.516, and it represents our final answer. Here, we analyze the time complexity of the algorithm. The time complexity is determined to be O, n asterisk target, where n represents the total number of coins, and target is the number of heads we aim to achieve. This arises because the algorithm employs a 2D dynamic programming table, DP, which spans dimensions of n plus 1 by target plus 1. For each coin, labeled as I, we iterate over all possible head counts from 0 to target. For each pair of indices, I, j, we perform a constant amount of work. This involves updating the probability values in dp, I, j, using data from the previous row, specifically dp, I1, j, and dp, I1, j1. Since there are n plus 1 in asterisk, target plus 1 iterations in total and each requires constant time, the overall time complexity simplifies to O, n asterisk target. Now, let's turn to the space complexity. The space complexity of this algorithm is also O, n asterisk target, primarily due to the use of the 2D dynamic programming table, DP. The dimensions of this table, n plus 1 by target plus 1, dictate the memory usage, which scales with the product of n and target. Each cell in this table stores a floating point value representing the probability of a specific outcome. Beyond the DP table, the algorithm uses only a few additional loop variables, which require constant space, O1. As a result, the memory usage is dominated by the size of the DP table, confirming that the overall space complexity is O, n asterisk target. Let's compare this dynamic programming approach with a brute force method. A naive brute force solution would involve simulating all possible outcomes of flipping in coins and counting the cases where exactly target heads occur. This would require enumerating 2 to the power of n possible outcomes, leading to a time complexity of O, 2 to the power of n, which becomes infeasible as n grows. In contrast, our dynamic programming approach is far more efficient, reducing the complexity to O, n asterisk target, by avoiding redundant calculations. Additionally, the best, average, and worst-case scenarios all share the same time and space complexity since the algorithm systematically fills out the entire DP table, irrespective of the input values. This consistency ensures predictable performance across different cases. To solidify our understanding, let's provide a mathematical justification for the big O notation. For time complexity, the nested loop structure results in n plus 1 asterisk, target plus 1 iterations. Since each iteration involves constant time operations, such as updating probabilities in the DP table, the total time complexity is O, n asterisk target. For space complexity, the DP table requires n plus 1 asterisk, target plus 1 entries, each of which occupies constant space. This leads to an overall space complexity of O, n asterisk target. In summary, the dynamic programming algorithm offers a substantial improvement over the brute force approach by reducing redundant computations. With both time and space complexities at O, n asterisk target, the method is efficient for moderate values of n and target. However, it's important to account for the memory usage of the DP table, which can become significant as n and target grow larger. When tackling this problem, there are a few common mistakes to be mindful of. First, using integer arithmetic for probabilities is a frequent pitfall. Since probabilities are decimal values, integer arithmetic will truncate these values and produce incorrect results. Always ensure you use floating point arithmetic for calculations. Next, the base case in dynamic programming is critical. DP 0, 0, representing 0 heads with 0 coins, should be initialized to 1.0 because there's exactly one way to achieve this, by doing nothing. Another issue arises from rounding errors in floating point arithmetic. When working with probabilities, cumulative rounding errors can accumulate, so it's important to minimize unnecessary intermediate computations. If precision becomes a concern, consider using libraries designed for higher precision. Lastly, when implementing the DP transition formula, make sure to account for all cases, especially for DP, I1, j, when j equals 0. Overlooking this can result in index out-of-bounds errors during execution. Efficient space usage is another key consideration. Many implementations store the entire 2D DP table, but this can lead to memory issues for larger inputs. Instead, you can optimize space by storing only the previous and current rows at a time, reducing memory usage significantly. From an interview perspective, this problem is a classic demonstration of dynamic programming principles. Understanding how to recognize overlapping subproblems and optimal substructure is crucial. Additionally, being able to clearly articulate the DP transition formula, explaining how each state depends on whether the current coin contributes to a head or not, can impress interviewers. Discussing space optimization strategies, such as reducing complexity from O, an asterisk target, to O, target, shows a solid grasp of trade-offs. Finally, addressing edge cases, such as target equals 0 or when all probabilities are 0, highlights a thorough and careful approach to solving the problem. This problem also shares similarities with several related problems on LeetCode, such as number of dice rolls with target sum, coin change, and knight probability in chessboard. Exploring these problems can deepen your understanding of dynamic programming and probability-based approaches. Beyond dynamic programming, there are alternative techniques you can consider. For example, a recursive approach with memoization avoids recalculating overlapping subproblems by storing results. While this method is often simpler to write and implement, it can introduce higher function call overhead compared to iterative DP. On the other hand, iterative dynamic programming provides a bottom-up approach that is generally more efficient in terms of both time and space. By employing space optimization techniques, iterative DP can handle larger input sizes more effectively, making it a practical choice in scenarios where resource constraints are a concern. Another alternative to consider is using Monte Carlo simulations. This approach involves simulating the coin tosses multiple times and estimating the probability based on the observed outcomes. While this method is conceptually straightforward and relatively easy to implement, it comes with significant trade-offs. Monte Carlo simulations are less precise than dynamic programming and become increasingly inefficient as the input size grows. This makes them less suitable for scenarios where accuracy and performance are critical. However, the technique can still be a valuable tool for gaining intuition about the problem or validating the results of other methods. Understanding these trade-offs allows you to make informed decisions about which approach to use based on the specific requirements of the problem or the constraints of the environment in which you're working. Great job making it to the end. In this problem, we explored an interesting challenge involving probability and dynamic programming. Remember, breaking problems into smaller subproblems is a key skill for solving complex coding challenges. Thanks for watching, and don't forget to subscribe for more problem-solving sessions. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!